Yes, thank you very much. Shall I start now? Yes, sure. Again, just to introduce myself, I can speak here, right? I'm Chinapat Panwiswas from Queen Mary University of London. It's a great pleasure for me to be here today, and just to share with you some thought about what is the modeling of additive manufacturing, especially for metallic system. And before that, I want to use this lecture to actually give some mutual understanding about what does it mean by additive manufacturing, 3D printing, 4D printing, what are they, what is that actually. So I just, about the outline of the first talk here is about, we need to know a little bit about history, and then you will know that the concept of 3D printing or additive manufacturing is not new anymore. It actually exists here since 1800, something like that. But the way we do it differently, to make it, to use this concept for manufacturing is actually relatively recently, about 50 years. And then after that, we will look into what is the difference in terms of after Industrial Revolution, what is the difference from the traditional manufacturing processes, and then what is the market and opportunity, that we have, and as well some challenges. So this lecture tended to be kind of rationales or some fundamental understanding of additive. So I just look at, this is actually released just today morning at time of India. And then I have seen Indian UK government program that want to have a collaborative project. What I can learn, actually, don't look at anything, just the figure here. You will see that that means the future. We are talking about the future, right? Future is about green, is about solar panel here, is about wind turbine here. And this actually create an opportunity for, it's not just UK and India, but it's actually global opportunity that we can looking forward. One of the argument of additive is actually, is that word investing, because it's quite energy intensive process. But sometimes if we understand the process very well, that is the objective of the course here. I believe additive is one of sustainable manufacturing processes that we can actually leverage the knowledge from science in order to technology take up. And I would like to start with something, future. So this is the future that people thinking of. I just borrowed this video from Siemens company. Yeah, you will see from CAD model to actually numerical simulation, and then going to the digital twin, that, engineering-based simulation things. And again, this is a kind of design of manufacturing. This is 3D printed part. Again, this involves simulation, again, the CFD, star CCM plus here for computational fluid dynamics. And this is robotic, robot-assisted manufacturing process. Again, this is subtractive manufacturing process that you can learn here. The forces that push the robot away from the milling pad can be calculated and compensated in real time, keeping the robot in its path. When it comes to operation, digital twin can compare the sensor data of a real point in real time with the simulation of its point. The availability of the point parallel to operation can be reliably predicted, and
sudden disruptions become a thing of the past. But this is just the beginning. And
this is just the beginning.
The future.
And
Digital twins with artificial intelligence allows computers to independently.
and then you will see previously the composition that they have titanium or whatsoever. So just want to. This is automotive application.
The digital twin breaks the traditional paradigm and opens up extraordinary possibilities. That's why digital twins are the innovation backbone of the future. Teenage ingenuity for life.
Yes, and actually this is about digital twin. It means different from different people, but in order to go to that future technology, the digital twin of those fancy components, we need to understand what happened in the material scale. And what I'm going to say today is about how to link material and the process together. And that is the next slide. So the outline of today's talk is about material manufacturing. So manufacturing is not just manufacturing. It's need to know about material as well, because additive is a process-sensitive, manufacturing. That means you need to understand what happening during additive or manufacturing of metal. What is actually people do in the past, and then we will learn from that as well. And then some concept from material and metallurgy perspective. How can we actually print all the jet engine, for example? That is the question that people are trying to achieve. Some of them show already in a small scale jet engine. They print them all using additive 3D printing. And then basically the concept or the talk in the next few days will focus on powder-based fusion process. This is one of the 7 additive manufacturing families that are following the ISO standard that I was going to talk to you. What is the fundamental of that? Why is so concerned? Why is so interesting as well? So paper published in Science and Nature talking about closing the gap of 3D printing with the material, for example, that you may see in the recent year. And then what is the perspective for me that set the scene for the next few years about data-driven modeling for additive manufacturing? And then I will summarize the first talk, introductory talk later. So what is the material manufacturing actually? So when you say about material and manufacturing, it seems to be something related, but normally people seem to neglect both of them each other. For example, it's evidenced by the department. They will have department of material and probably manufacturing or for example, or even mechanical. I think it is important to not to separate them, but to study this, what does it mean about material science? Is actually study the relationship between composition, process, structure, rising from the processing that you do, and then subsequent porosity and the performance. And this will understand this to improve and minimize or unlock the potential of the material that you use to give the maximum or full potential for that. And then normally we will use different processing technique or methodology for different material. 3D printing is one of them, using across not only metal, ceramic, polymer, composite as well. So it gives flexibility of the design and also opportunity. But again, in order to make it first right time usage, we may need to understand the process more. And this is about the course today. So for example, I said to print the whole jet engine, this is the dream. So this is a powder-based fusion process when you have the powder here, and then you use the wiper here to spread the powder, and use a laser to fuse the powder layer by layer until you get the 3D structure. I think this concept don't need to explain a lot, but why is actually 3D printing? If you look at the inspiration from the industrial revolution concept, that the first ever, is around a pre-Victorian age. You know that people knowing about how to make iron or steel systematically, but even prehistoric time is a lot known already. And then when the first introduction of electricity came toward beginning of 19th century here, refrigerator and mass production come, and this is where the new ways of producing things. I think I just want to emphasize this, and then when we have another third wave of this one, when we have the new ways of this by electronics and automation process, I mean, a little bit robot coming in now to change the way we manufacture things or we making things. And after that, I mean, just very recently, artificial intelligence, nanotechnology, including material science and 3D printing, play a role to revolutionize the way we're making things as well. So from just electronic or automotive, we make something better rather than waste a lot of materials by about 90%. I will talk to you more later. And now we know how to make better or make the, how to say, calculation faster by quantum computing, for example, that you see. And this will be vision into the 2030 onward, from my opinion, or even starting now, Industrial 5.0. I mean, I don't want to talk anymore about 4.0 because we need to look ahead when we have two important words, which is sustainable and human-centric. That means the interaction of human and also sustainability is an important factor for AI and then data-driven model or data science in the future that we use to making things better. And this is the picture why 3D printing gives the opportunity that projecting ahead to that direction. And what and how can we go into that? I mean, just a few slides, probably boring, but just is about setting the scene that this sustainability aspect actually contribute to the Sustainable Development Goal here, number 9, industry, innovation, and infrastructure, and also the responsible consumption and the production. This one align very well with the, I mean, how to say, mutual goal target for the world to moving forward. And having said that, it's not only, it's one I give the example from other country in Eastern country as well, Japan. They define 3D printing is one of emerging technology that we need to create for Industry 4.0, but even they introduce a new policy for 5.0 already. And this can create a social and global impact in such a way that we manufacturing things. That is the importance of 3D printing. But the next step, when we realize this actually quite important of this, how can we make it? And then we need to step back a little bit to see what we have now. So for example, if you are looking at the 3D printed of the jet engine that I mentioned earlier, I would need to emphasize that this is the high value added part that some of you may do research in aerospace material. That your concern is about, for example, you may not be able to replace this investment cast turbine blade at the moment because it's actually, the strength is not compromised using 3D printed, but there's some way using electron beam melting that you can actually fabricate it in a single crystal. Again, a lot of research going on to make that happen. Or if we try to print this jet engine, you may need to think about other components. For example, the first pieces of the 3D printed part are flying in the air in 2012 by, what is the company, a GE? Yeah, it's actually a fuel nozzle that I will give you some introduction later. So in this one, that means we need to understand not only the what is that require engineering requirement, but also we want to know to place the material in the right place in order to make it, robust and then manufacturing it in such an efficient way. So this one, we hope that 3D printing can revolutionize or change the way we make the jet engine. But just keep it in mind, and my question to this is that how we print it. And we print it without defect, because if it actually contains some defect, you're not going to find defected bread to carry 300 life. It's not good, right? So we need to make sure that in terms of material science, metallurgy, and also processing, that around this to make it more regulated or standardized this one. So as I said, existing, people talking about 3D printing, but you will see this is slide borrowed from NASA's, right? Talking about, okay, you get a lot of defects, especially when you print a big part. And this is why we need to know and warn you that it's not that easy, just not like print polymer, resin, or some other component. But printing metal is something challenging and something that we need to take care of from scientific perspective. So if we looking at, as I said, metal or metallic 3D printing, I said before, so you will know that every time we discover or we actually knows how to make things, and probably at the very early stage, I mean, Indian has done very well with the casting or steel making, as you know, you have a company on that. And then what I'm going to say is that every time a new era comes, the age of, let's say, Stone Age, bronze, iron, or steel, and then superalloy, which is the high performance or heat resistant material here, you will see that they will have different, I mean, how to say, important or requirement for different smart or advanced material. And then now, this is the birth of, you may heard about high entropy alloys, but again, this is just the way we want to map all the material, I mean, spectrum in this one chart. So the future is going to be something like a lighter, stronger, or weight, strength to weight ratio, which is reduce the weight, but also keep the strength, and how can we make it? So Professor Kumar may talk about design of experiment for metamaterial structure or lattice structure later. Again, when we understand, we want to understand this. Why? Because when you print titanium and print nickel or print shape memory alloy, it's probably totally different story. So we need to understand material science first, as well as the processing of it. So this needs to come into package. So, and then this is a summarize of one example, actually, superalloy. Are there anyone here knows about superalloy? High temperature material, heat resistant, I mean, high resistant in degradation, right? Like creep, fatigue, blah, blah, blah. So superalloy is one of the, I would say, the most clever materials on Earth. I mean, it's about 80 years old now, since its inception in about 1940s by investment casting. But again, the graph here show that for when you introduce a new process like directional solidification, single crystal casting, or powder metallurgy, you usually introduce a new composition or new material to actually optimize for that process. So it means that, I mean, this is actually as an example, like casting. This is likely to be first generation superalloy that optimize for casting, which is MAR 200. And then you have directional solidification, which is actually polycrystalline structure, CM247 LC, but the people trying to print 0247. I would say, what is the problem? And then single crystal, this is the CMSX4, which is second generation superalloy. And again, each composition here optimized for the process, and that's work, actually. Even people trying to replace CMSX4 with high entropy alloy, but when you consider all the factors, it's not really happening yet, because it doesn't worth investing in the new composition which doesn't have superior combination of the property like existing material. But my question to this slide is that when you have new process like additive, which is actually not news, but introduction of additive to the metallic printing around mid-1990s or about 2000 millennium year. So it's actually, the question is that, can we use the existing material, not only superalloy, existing material using the new process? The answer I will show you later is probably slightly no. That's because of when you decide the composition for each process, you think about a different criteria, or if you like, you engineer it differently. So that's why we need to both understand metallurgy or material science and then processing science of it. And then before we go into the process, I want to give you some, how to say, inspiration about 3D printing, about the process we call additive manufacturing. What is that? And then if you take the definition from the ISO ASTM 5290 here, you say that the process of joining material to make part or object from 3D model using layer by layer as opposed to subtractive or formative methodology. So I will give you some example later what does mean by subtractive or formative technology. And actually, as I said before, additive manufacturing has a 7 process family or category that listed here. So apart from that, it's actually fall into all these 7. Believe me, everything is all. You have a lot of, abbreviation, but it will fall into these 7 categories. So binder jetting, I'm not mentioning much, but for example, desktop metal provide the opportunity to basically you deposit your binder onto the metal powder bed, and then you create a green part, and then you sinter later. So direct energy deposition is actually used a lot now, or one of them is a WAM or wire-arc additive manufacturing, that you use a wire and then melt it layer by layer. For example, to repair a turbine blade or wind turbine, for example. Metal extrusion is actually similar, but not the same. It's similar to the, what this is called, in sintering we have the, in certain, I forgot, but it's actually similar to MIM process, metal injection molding. But that one, actually you have a mold, but metal extrusion, you don't have a mold, you just extrude your material when you combine your binder and your material together. This can be used for metal as well. Metal jetting is actually you deposit liquid metal, for example, if it's metal, or you deposit some material and then created the 3D structure. Powder-based fusion is something we're going to talk a lot. Previously called selective laser melting, but the standard now, even in the publication, we no longer use selective laser melting. Additive Manufacturing Journal will be rejected based upon that because you don't know, it's now have to call powder-based fusion. But sheet lamination is also another process. It's not very popular research area, but there's something there. And then actually this is wet photopolymerization, or you use a stereolithography that people use a kind of light to fabricate the lace in the liquid bath, something like that. I will show you something. This is probably for bioprinting mainly. But the thing just want to say is that this is the things. Additive actually happened, the concept I would say, since 1860 in the photo sculpture here. This is a prehistory of this kind of idea or thought. And then the milestone, the first patent filed on the 1868. Believe me or not, this is actually about 50, 60 years, or more than 60 years now, since the inception of the first additive machine ever that you have. And then they commercialized is about 40 years ago, nearly, 1987. It's not new technology, but the way you make this one innovate, the way you make the material in the jet engine is probably new. And then you have the first metal printer prototype in 1994. It's just P-Millennium. And then the first is on fly, which is by GE in I would say around 2012 or 2013, but around that. So this is entering the modern additive manufacturing, which we are talking now. So he's quite important guy as well. This is, I think you know EOS company by Germany, right? Or US, I can't remember. I'm not experimental guy, but he's the one who looking at the very first model of the EOS machine back in about this period of time, about 30, 40 years ago. So the prehistory of the photo sculpture, I'm talking about here, and this is because, we're looking at the US patent back in 1864. Actually, you have something like this, that you try to basically add material bit by bit. That time is not layer by layer that yet. But this is a concept of additive. You not actually machine something out, but you add something in to create some structure. And this is we call this a prehistory time of additive. And later in the topography, you will see in about 1925, you actually has the way to manufacture this contour map. So the way you do this, you actually add layer by layer. Like this is kind of Lego pieces that you build a kind of mountain or whatsoever you can imagine structure here. And this one is likely looking like additive. You add layer by layer, and then you create some 3D structure here. But the mesh size here or the pixel that you deposit is quite coarse in this sense. But let's imagine this is just 1925. And this is the next one is a pattern on the, material deposition actually filed to make a new decorative article here in 1925. And after that, in early stereolithography, the first ever, patent that to build a two-laser system, now we use laser to build a 3D construction of photosensitive polymer. Okay, it's actually start in the material polymer. So this process optimized for polymer. That is the message. And then this is the method that, and then along with the apparatus scheme or drawing that show how to make this construction, this production for this polymer using two laser here. Again, this is the patent granted in 1927. So I will base the date on this documented evidence here. So that means this is probably can say very early stage of, modern additive manufacturing machine or manufacturer. So next one is about one Japanese guy called Dr. Kodama that actually proposed something on the new 3D printing. Again, it's based on the idea of stereolithography, coincidentally. And then he needs to actually withdraw his application for patent because of funding issue, something like that. Because as you know, to apply for US patent is actually a lot of money, is our investment, right? To let the world recognize. But after that, there's some people actually look after, which is actually Chuck Hall here, just find the pattern. And please remember the name Chuck Hall is the very first one who actually commercialized this and then probably billionaire now. So in 1984, it's not too far from here, it's exactly about 40 years, right? 1984. So this is the first origin of the manufacturing of the 3D printing in metal now. So I probably think that the same concept applied to the Professor Kumar lab as well I visited yesterday. So this is charcoal here in front of his first commercialized available AM machine in 1987. And this actually someone said to me is that going to be a very expensive process. If you talk about additive manufacturing or 3D printing for some high value added part, it's not going to, you're not going to waste your money to print something doesn't actually have some, value, right? Because additive is for a niche application, like implant, like something that, not construction for sure. We were not going to print metal for construction. But if you look at, for example, in automotive area, like in the motorsport, for example, or luxurious car, you see that the designing of the car actually more expensive, twice expensive than the manufacturing cost itself. So they suggest that actually manufacturing, when people say that additive is so expensive process, it's probably not true in some areas. So the answer to some of my previous colleague question is that we need to select the correct application for metal 3D printing. We're not going to print metal for everything, but it's actually some area which require kind of delicate care for that, like blade, or in aerospace, some automotive part, So that means engineer, material science, and mechanical engineer or computer science need to be involved to move this field forward. So I would like to give some review of the method, give you some context about different modern 3D printing technology. So the first one is, the first one is stereolithography or SLA. I believe you know, or every lab, probably in your lab here you have this as well. It's small and an affordable machine that every university can have it for students to have a project with. So this is just a light, and then you have a resin, put it there, probably heated substrate, and then you basically have a liquid bath here as well later. So this is affordable kind of machine that may be useful as well for bioprinting. This machine can be adapt to use for kind of tissue or this kind of printing as well. But this is some research need to be going on. Again, that's what I said previously. Need to select the material along with the process that we're going to do. So in this case, it's probably not for metal. But anyway, that's just to review, and this is called wire-based additive manufacturing. When you deposit the material, this is the laser nozzle, right? And then you use arc wire, this is wire arc additive. So you add it layer by layer until you get the 3D structure here. So this one we call near net shape manufacturing as well, because you don't need to do anything much after that. It is a slow motion of these things. But you will see that will still have a problem. You see a balling effect or surface roughness here and a melt pool whatsoever. But this is something to concern next lecture. Don't need to talk about now. But you see layer by layer here it's like making a cake. We call cake, right? You add layer by layer, and then you get the pieces of cake here. And that's an example. The next example is actually powder-based fusion. This is something we're going to focus on in the next few days. And then you have a chamber here. You have the powder feedstock here. You spread the powder onto the substrate. Whatsoever how many substrate you have. And then you swipe it another direction, and then go into this used powder. And you use laser to fuse them layer by layer until you create a 3D structure. In this case, I think it's probably a turbocharger for automotive. Again, this is a delicate part that usually you use about 40 manufacturing steps to manufacture, but you reduce it to one without waste. That is the key idea. But the things that control the quality of this part is actually the laser matter interaction, which we are going to focus in the next lecture later today. You see now a lot of spatter and everything coming out. And this one, when you remove with care, and then you will get the part 3D printed. Again, the health and safety issue here is probably delicate, and it's expensive process. That's why I said we're not going to print this one for microphone, for example. It's too expensive. But if you want to do it on purpose, probably yes. We need to be careful about that. And then you get this part, and then you will notice that this video very good. Actually, you can see that there's a surface roughness and support structure associated with that. Again, this requires a lot of not only metallurgy but also engineering, mechanical design of experiment to allow this happen. So if we summarize in a very quick short for this one, you get the pro of this process. Actually, you get a near net shape of complex geometry. That is why you use this process. And then you can do rapid prototyping on this one. You get, if it doesn't do something wrong, it's actually, we expect it to get less scrap and waste when you know the condition well, how to do this. And then the con or the disadvantage of this process, actually, the feedstock at the moment is still expensive. If you talk about high quality feedstock, especially for biomedical implant or medical grade implant powder, it will be expensive. Titanium, for example. And then defect rate is still high, but this is the way why research is important to reduce that once we understand the interaction of this in the material. And then resource stress is actually another issue, people looking at that from the composition of material, processing, structure, and property perspective. This one is become issue, but now a lot of research going on trying to make it possible. Like for the material structure, that you can design a lot of property out of the range of the bulk property. That is the concept that is not possible using only CNC approach, that you cannot get the internal structure in a micrometer length scale, something like that. So that's why application of this is so related to the process you are going to use. Next one is actually, to recap, that is additive manufacturing, but now we are going to talk about how can we replace those traditional process, or even we cannot replace, is to understand what is the traditional process for metal manufacturing. So we have forming, casting, joining, and machining. I would like to make some big difference of joining and additive manufacturing. Joining, you don't need to add material sometimes. If you don't use filler material, you just use some power source and then fuse them together. We call joining. The difference of joining and additive is that additive is add material and join them together. So that means, in my definition, welding and additive are different. But people may say it's the same. But anyway, I will show you why different later. In the probably by lecture 8, you will understand why I make it different. So this is forming process, and this is a big forge hot ingot machine here. You will see, probably you sit in the steel manufacturing plant, and then after that you punch this. I mean, I believe mechanical engineering also need to learn about manufacturing process like this, right? You upset of this one, you get some skin of this manufacturing, you punch it, you force it. And then the way you force it, and the temperature and whatsoever, and then you drill the hole to do the ring rolling later. So in a very hot state, you drill the hole, do ring rolling later. You will see that this is do with care. And this process has been done long time ago. It's not just new process at all. A robotic or robot-assisted additive that you talk is actually use something already exists to do things here. And after that, you roll it. I mean, this one I want to say later that this link to the microstructure development. The way they do is actually make the near uniform grain size in order to get the property across the section uniformly. Otherwise, if there is some weak area, you won't be able to, make it fly. For example, if this one is a disc, or this one is the ring for engine, for example. And that is the thing. So, and later in the probably next lecture or the lecture after next, you will see how we simulate this process to get the correct stress, thermal and stress field in order to get or optimize the process to get better understanding when you want to change the material. Let's say from steel to titanium for a jet engine component, for example. And this is the thing. So if I summarize this, we call this is a subtractive manufacturing process. You will say that because it's subtract, or they actually you waste a lot of money. Money and also material as well, environment as well. Microstructure supposed to be uniform. That means it's quite robust process that's used in the quite high value added manufacturing company. And then the mechanical property, I mean, given that the structure and property are strongly related. So if you get the grain size, according to Hall page relation, you may get the similar strength across the section, something. That is the ideal, but in reality, things like that need to be optimized. But anyway, that is leave it for another matter. It's not additive. This is just to make the difference. Large production is actually correct, because you can do in the bigger scale, not like additive that you can now only doing it in small scale. But again, it's about the application that I said. The disadvantage is actually this equipment, the toolings are expensive. It's only big company can afford it. It's not possible for SME or smaller company to do this. And process difficulty is actually another problem because you need to use a robot algorithm to program it from the final shape. It's actually relatively simple, but actually hide it in the value. You need to have the kind of structural integrity for this part, so you want to control it in a robust manner. So this way you will use forming. I mean, forming, I will have another diagram to summarize this. Forming, that's one of the, forging is one of the forming process. And then you know, you waste about 90% of the raw material in this part. You get only 10% in the final product. And this is not sustainable. This is one of the subtractive manufacturing process. I did comment as well in my NatureCom commentary back in 2020. So next one is casting. So that means you use some heat source to heat up the metal, and then you pour it. In this case, in this case, it's actually aluminum alloy, and this one actually is sand casting, I believe. And then this is uses for automotive part. I mean, complicated, and then surface finish is good. You say this is a liquid aluminum here. And after that, you will see how things solidify. And you see some shrinkage later as well. Yeah, it's level up here. Stop. And then they start to solidify and shrink a little bit to the central here. And later, later you will remove this part. I mean, again, robot is used for this kind of purpose. And then you get quite complicated geometry for this process. And then you see this is automotive part here. Again, again, this is ideal. This process is ideal for complex geometry, good surface finish usually. And then the con of this one or disadvantage is actually equipment is so expensive. And you probably some way, somehow, you compromise the mechanical property. Again, if you notice from this, that means previous process may related more on the solid mechanics part, and this one is actually more fluid. So because you have the fluid, actually liquid metal as a fluid, and flow into the mold. So please keep this in mind that I will use this later. And next is actually joining. We as I said, welding. This is a torch welding in this case. So you weld it. I mean, you have some probably material here, and then you melt it or in a specific location, and then you join them together. Or you use something called or you use something called and this is the structure that you will see after that process. And then sometimes you don't need to have any material to join them together. You just use a frictional force, I mean linear friction actually, or rotational welding, friction welding. So you rotate the material very high frequency until this to create a kind of joining area, not to melt ideally, but actually these two pieces will join together. And that is the things we call welding integrity that you want. The weld, which is the weakest area, due to the microstructure in the joining part, are different from the parent and the heat affected zone. So this one, the phase transformation kicks in now. So the base material, heat affected zone and welded zone have different microstructure, which subject to different property. And then you may get the weakest zone in this area. And this may be an issue if you don't actually manufacture with care. That is to summarize this one using for probably repair or rejuvenation of the material. And then mechanical integrity is important. You can use this for this similar material like steel and nickel, for example. And then for the advantage of this, you may create some residual stress, especially in this zone. And this is the weakest area. Actually, you need to be actually take care of this area. The local microstructure, I mean, in the weldment zone is changed. So you need to look after this very carefully in order to get the property right. And then fatigue and distortion of dynamic loading will be important if you doesn't make this right. And this will be the failure area for the, let's say, flying engine, for example. Last but not least is the machining. It's actually not very, I think it's inclusive. So I think you know a lot if you're familiar with 3D printing. I mean, machining is kind of CNC kind of approach that we use the machine here to remove the material, to get the shape that you want. Again, the remaining material that you want is probably only 5 to 10% from the first raw material you use. So this is not sustainable, but we use this for long time. But the way to make it sustainable, probably dealing with a scrap or swap material that you're going to use for future application, for example. But again, this is machining, traditional, typical, every country has it. And just summarize, the surface control of this is very good. And then you get a net shape on very net shape because that's what you want, like a screw notch or whatsoever. And this is a destructive, not subtractive, but not, it's destructive and subtractive. That means you destroy material and then you remove it. And this is, as I said, most of the product require this kind of precision. Some company call precision manufacturing, but again, this is not very new manufacturing process. But yeah, anyway, just to make you aware of this. But if you compare additive with traditional manufacturing process in terms of economics, you will see that the cost per unit pieces for traditional is actually, if you do very small quantity, it's so expensive. But if you do kind of mass production, the cost per unit pieces is actually very low. And this is preferable for company, right? But additive, actually, this cost per quantity is not very much different. So it's kind of very straight line. So even you make 1 or make 1,000, it's relatively the same. But again, the way you make it without waste, this is important. It's not just making it. It's about whether or not you have a robust approach to do it correctly. There's a break-even point here. So this is not going to work for traditional process, for example. You're not going to make mold like this complicated shape. You may need to use another approach. So the new design of this, with the new design and the additive process, you may be able to shift this one to the right, but again, it's not comparable with the, I mean, you shift the break-even point here, but anyway, additive still better. So if you compare about the cost with the complexity, if you have a very small complexity, your cost is not a lot. But if your part is so complex, that means traditional process like you use CNC or machining is so expensive. But additive is relatively in different direction of this cost per quantity. When you have more complexity, the cost will be slightly increased. It's not massive. Again, we may need to design with care on the design of manufacture or do some analysis on thermal management on this part in order to get with the minimum stress distortion, for example. And this is perfect for using this kind of process for metamaterial design. And this metamaterial, which is the future of manufacturing, that actually the idea of this is actually you want to produce a new property that far away from bulk property. Example, very good nice research from Professor Gruma lab, having a titanium. The bulk property, probably you have elastic modulus about 100 gigapascal, but with metamaterial structure, you can lower the stiffness by 2 orders of magnitude. You can achieve about 1 gigapascal on purpose when you do correct design of experiment. So I believe you will hear more from him later today or tomorrow whatsoever. But again, we also use this one during very difficult time in the past 3-4 years in COVID. So the goggle here, we printed by Additive, so fit for different, people around the world. So for example, in Asian country and European country, you may not be able to have one size fit all. So that means this may be useful to print this one. And then definitely this kind of 3D printing concept had been used in the production line assembly already. And then again, for this one, you don't need to take care much. Even it's important for life, but it's not flying component, right? You can use, has a knowledge barrier, and it's timely for this pandemic in about 3, 4, 5 years ago. And then the con of this one is cost ineffective that time. It's still now, but we need to find new business model to make it effective. And then the production rate is very slow. Even we can actually use this fusion metal additive to produce this part, but still relatively slow with a conventional process. But by the way, we get more personalized, and also this is the future. Sustainable, personalized, and all these things. And if you look at in terms of the market or economy, the patent actually filed, from Additive since what I said, the first manufacture the machine in about 1997, 1980 something, you see is increasing actually in terms of the patent from about 50 to now. Now it's more than this. It's actually shooting up to about 1,000 now. So your cumulative of this is a lot of patent actually in the AM industry. So in short, additive manufacturing industry. But the application submitted is far more, 3 times more than there's something accepted or issued. Anyway, it's still an opportunity. So in terms of product, you will see that they anticipated growth. Again, this slide is relatively old in 2019. So it's growing in 2018 by 33%, 1/3 of the sector. It's quite a lot, and this is in the service and product. The product is in blue. You will see that more and more AM part is actually receive some attention or realized by industry. And that's this opportunity that Professor Krumar mentioned earlier today, that we may anticipate about 80 billion market for additive in 2028, right? So, this beyond the graph by 10 years. So, again, now is more about what is the AM or additive manufacturing in metal, find its application. In automotive, aerospace, and tooling, this is some example in automotive. BMW, has been used this for printed some wheel. Again, this is a luxurious car, so you do it on purpose somehow, but some part like a turbocharger, they use 3D printed now, a lot of research. I think I can say that I evident that 10 years ago that they have a big automotive company approach to us in Oxford that time to research on the automotive part for 3D printing. But having said that, you see automotive part, you have a lot of part that's now been 3D printed. So it's not just speculation now, it's real, it's happened. And this is the first the full nozzle for jet engine. Again, this is fired by GE. So this is the steel, I think. And then in terms of tooling or something complicated, you can design using additive here as well. So more than that, you also have some application in biomedical implant. I think we will hear more from Professor Kumar from a case study or application. And then you also have some game avatar or something like that. This is also a big market as well for entertaining or whatsoever, as well as the jewelry. It's a lot of patent file in this area. Especially, I would like to share with you some colleagues in UK did file patent to fabricate platinum, actually successfully using some nanoparticle. So this is something still going on. The research is a lot that we need to do more. Again, that is jewelry, so that means small amount, delicate part. Again, that is the application. Or this is the architecture or display, which is actually you never ever before can. You have to do it by hand, piece by piece, but now you can print it. And this one will be useful not only for museum display or architecture, but it may be a prototyping for assisting a medical doctor for the learning or studying in a very complicated channel. If you use the X-ray 3D scan and then you print it at some sensitive location, this 3D printing proof is useful for education as well. So it's a numerous opportunity for 3D printing, from design, as I said, ultra delicate component or geometry, rapid prototyping. You also shorten the design cycle as well. And also you actually, you don't need an unnecessary assembly if you want. If you see here, this is a bone. Let's say if someone has an accident, has a bone fracture, and you want to print something that has the bone match with the cancellous bone with the low stiffness using titanium. Now, probably it's possible, but it's still in the lab, not in the commercialization. But it has an opportunity that we can design mixed with material science, metallurgy, and processing to make this happen for the near future. And then the manufacturing economy is actually free from large-scale equipment. And then you don't need a large-scale equipment to fabricate this. As, for example, you may invest probably $250,000. It has to be that scale, unfortunately. It's still no cheaper than that for the decent, for research and for high manufacturing part, or probably up to $1 million with the full option machine. But you can do more than you can anticipate it. Yeah, and then no less machining or tooling or waste. And then this production time is actually reduced if you know process condition well, what is the right process. So the business model for the next additive manufacturing industry is that it's not just sell the the machine itself, but it has to come with package saying you have a material A, which is titanium, and you need to come with a processing window or processing route that to make it work for some application. So now, from now onward, the business model will be like that. So they will sell with a precise window for you to choose, but impossible because sometimes for the company intellectual property, it's impossible for you to review that for them that I want to do this in the future. So that's why we need to have some knowledge if it's not in mass production yet. So during the intellectual property or secure process, so you may need some material engineer, computer science, physics, chemistry, blah, blah, blah. But anyway, this is still opportunity. So we use this as well for the repair and overhaul in transportation. But also in aerospace, it's more and more. I have a project with the aerospace company looking at using the Y-based additive to repair some turbine blade part, for example. So this is coming. And in space manufacturing, that you may see the program from NASA that they try to print something in space. It's also possible now as well. There's an experiment going on in this area. If I remember correctly, led by Purdue University or Carnegie Mellon, for example. And then you have the material property. You can actually tailor it as much as you can. This is all about my research. So if you understand the interaction of material and the heat source, you may be able to tweak or fine-tune the material locally. So the ideal cases is that you can do like fine structure here, coarse structure there, or something mixture over there. Because the different part require different property when you design it. But with traditional process like forging, you'll not be able to do that easily. But additive provide you opportunity to do that. Or you will have some or material structure for additive because the signature of this process actually rapid solidification. So we may use of this to leverage the use of this one for specific application like in electronic structure, for example. Electronic devices, not structure, yeah. And then you can do even graded material or someone called functionally graded material. That means you have slightly copper there, more steel here, and then slightly or graded, like that you will have a shredding of the material, which is not possible before without additive manufacturing, right? So this is an opportunity, but still there's a challenge that we need to overcome to get this opportunity possible in the long run. Let's say this is the disk. The idea is that we don't want to have non-uniformity in this disk. We want the disk here has a single kind of grain size throughout, which is not possible traditionally. But we hope additive can offer this opportunity to manufacture that. So this is the challenge. Having said that, I just want to, probably that is the very first part of the presentation. And next is actually how can we summarize all that in the context of material and manufacturing processes. So from this one, I just want to show that the way you print jet engine component or the way you print some stand for your material, for biomedical, is actually physics is the same, but the way you implement it are so different. So you need to take care of, even you are dealing with titanium, let's say they're both titanium blade, and then the titanium 60, they use both the same material, different grade anyway, but we can transfer the knowledge of the physics that going on, but in terms of the property, for medical, you may concern another factor on non-toxicity or bioactivity. But for aerospace, you concern more about structural integrity, or blah, blah, blah. Again, that's what I want to say. We need to, when we say something printing titanium, it's not just titanium material that we're talking about. We need to say, along with that, we need to talk to yourself that is what is the application you are looking for. And now, we're going to summarize what I just said in the probably 70% of the talk this lecture. So we have in the category of the metal 3D printing or metal additive manufacturing processes, we have powder-based fusion, which is one of the standard. We have direct energy deposition. We have solid state formation like lamination, sheet lamination. So the feedstock associated with that, definitely this is powder. The feedstock will be powder for sure. And then you may use different process to process this powder using the heat source of laser heat source or electron beam heat source. Again, they are so different in detail as well as in the physics, the way they melt as well. So this will be talking a bit later. Direct energy deposition. If you talk about powder feedstock, it can be a kind of array of powder deposit onto the substrate. This process known as a bronze powder process or deposition. And if you talk about wire, there's few options you can choose. I would say arc-based deposition or laser wire, electron beam deposition. Again, this depends on the heat source you use for that. Again, there's some detailed difference in different manufacturing process for different material. And then last but not least, the solid state. So you may use ultrasonic additive for foil here. Not much research from my side, or friction stir additive. I have some research on this. Or if you combine this and this, for example, this we call hybrid manufacturing. Again, this is leave it for the later matter. And then they still have other additive process like I mentioned, especially metal, they can use bi-jetting as well, material extrusion, jewel printing or material jetting, or even wet or liquid bath is possible. Again, we're not talking about that for the moment. We're just focusing on probably first two sections. I call this process like melting-based additive manufacturing. So you need to make it melt, make it liquid first, and then you join them together. And then how to choose this one is depend on different factor. I mean, from engineer, I borrow from NASA slide here, depend on the cost, material property, internal geometry, availability, scale of hardware, complexity of feature, and this deposition rate, and then the precision of the feature are also big consideration. Why people still using powder bed? Because they give at the moment the highest resolution for metal 3D printing. The resolution is the same as the powder that you use. The finer, the smaller resolution you can achieve. For example, now there is a new term called micro LPBF. That means you print something in the micro scale, sub-micron powder length scale for some electronic or some delicate part purpose, or even printing some notebook things. Again, for the arc-based deposition, the characteristic length scale is larger because the melt pool of that size is actually around millimeter scale. So you're talking about large component, but still you need to think about residual stress development or thermal management is key. So again, that we will go to in the different process and the science behind that later. So this is in terms of process, AM process. And then as I said at the beginning, we need to talk in additive manufacturing or AM, not only the processes, we need to talk about as well the material. So this is a summary of the material used so far, but not very inclusive, not fully inclusive in AM. When I say AM means the LPBF, using laser, LPBF, using electron beam, and then direct energy deposition. So you will see this is all metal AM. So from nickel, again, this is not inclusive, but you will see this one they prefer in US because they use for the NIST or National Institute of Science Technology a lot. This is for space application. Try to print this one, but proved to be quite okay. It's printable. Anyway, we talk about this later, and also Wasperoid. I mean, copper is also used or print a lot in the heat exchanger application. Aluminum base, again, as well, try to print some complicated part, but still aluminum is very high refractory material. That means we need to manage it very well. I mean, and then iron is a lot to print. For example, 7.4 pH. I think your lab also print as well 7.4 pH or 316 standard. And here, and then the titanium base. I mean, people trying to print Ti64, titanium 64 or gamma titanium alumini. Again, try to replace the superalloy, but I don't think it's not successful yet, or even some program already closed down because of the metallurgical defect or understanding about cracking. Again, cobalt based, you say cobalt chrome is also biomedical application as well. Refractory is attract more attention at the moment. It's hard to print material high temperature, high melting point material here, using for space nuclear application like tungsten, moly, tantalum. Tantalum also is my research is here for biomedical as well, tantalum printing, and also C103 actually is a new NASA program for niobium-based alloy for space application. Again, they use refractory, and then they have a biomaterial. As I said, you can print whatever you like. I mean, the lecture later, I will say one technique we call in situ alloying. We mix something using laser together. So we alloy them during printing. Yeah, and then you can do bimetallic. And also you have some metal metric composite. It's a lot actually. Very first paper in high strength aluminum alloy, they try to print it. Paper by Professor Teresa Pollock from UCSD, Santa Barbara. Also, again, this is the same concept as a casting they use in cornelane or particle to break down the microstructure. Anyway, this research still going on because not a lot information and also research for a specific application. Again, I would say this is an opportunity, and as I said, every example I mentioned is related to the application you're going to use. So I think this has to come in package. It's not, we cannot talk individually. So process, material, application has to come together. That's the key. And if we looking at again, nothing actually perfect. We need to understand what is advantage and disadvantage of this. So the component of this laser melting powder-based fusion, it will be highly complex and low production rate. But feature here cannot be fabricated by other method. For example, if it's so small, you don't have any machining tools that allow you to fabricate like in the sub-micron length scale, but additive may offer that opportunity, for example. So you can customize whatever you like. For example, in implant research, metal implant research, the aim is to do the personalized implant or prosthetic, for example. So want to fit for people. And then, yeah, this is a short lead time property. Actually now is better than cast, but actually a little bit lower than rod materials, but still improving. Actually, research need to be there. So weight reduction using material structure or lattice printing, for example. And yes, this is an advantage, but at the same time, you have limitation actually. So you limit by only some selection of material based on the understanding from welding. So weldable alloy, so sometimes printable. I prefer printable, not weldable, or additive manufacturable rather than weldable. But anyway, a build envelope size limit. Sometimes it depends on your build chamber. If you have a smaller machine, your printed or your component will based on that, limit by that. But if you don't have a big chamber, but I will show you probably one figure later in Formnext that they use wire-based printing. Formnext is happening, I think now or just finished in Germany. So they print 3-meter component using metal printing. So it's coming now. It's even, yeah. So for example, surface roughness is still issue because especially the rotating part that you require fatigue and then creep life. So you need to come with package again, not only material fabrication, but also probably a little bit processing, how you treat the process to make the part actually usable or robust. Yeah, build microstructure requires some processing, and then there is some waste actually generated from this or unused powder. How can we recycle it? It's another challenge topic that people are trying to do, using or recycle some reused powder. And also probably at the moment, the advantage from the economic point of view is actually more expensive than traditional process for now. I mean, yeah, but we think that in the near future, this cost will be reduced a lot, and then it will outweigh the traditional process for some selected or target application. Yeah, just to emphasize some first printed part, fly on air. So this is fuel nozzle by GE. I think this is made in 2012 to 2013, and this is actually weight 20% less than, because you use 3D printing. You reduce the weight by 25% for airline is important for the energy or fuel assumption, right? And then this is actually 5 times as doable. So it's more efficient. And the goal of this is not actually print one part, but we want to reduce assembly that's talked before. So each part here, print in one go. That is the aim. And this is the first 3D printed jet engine. This is a model, smaller version, printed by, I think, Monash University in Australia. And the team is Professor Xinhua Wu. Yeah, she print this part already. So it's not a dream now, it's happening. And this process, I mean, now this is about, probably this actually, in my intention is to use this time to prepare, because next session will be probably long. And then I'll try to introduce something first. So before finishing this, I mean, I think we still have time. Do you have any question at all? I think I speaking too long. Any question for now before move the last part? Just to give intro for the next lecture. Do you have any question? Everything clear? Good, thank you. So as I said, and then as the program stands, you know that we talk more on the melting-based additive manufacturing, especially the powder-based fusion additive process. So as I said earlier, the powder-based fusion, we have two heat sources that we can use, whether either laser or electron beam. Laser like EOS, SLM solution, I mean in terms of manufacture. And then electron beam is, for example, free melt company from, I think, Sweden as well. And then the basic process is for LPBF, actually layer by layer. The feature actually melted using laser and solidified. The key is laser and solidified. That means there will be some laser matter interaction, and then solidification will play an important role. The advantage of this process is actually, as I said before, this is the highest resolution 3D printing metal so far, so high feature resolution with the complex internal design like cooling channel. I mean, this diagram illustrates that printing process. But these advantages, as I said before, is limited by your build chamber. So the scale limit doesn't provide solution for all components. Basically, you cannot print everything. It's about the way you select it and then, which component to print. Electron beam process actually give the similar, it's layer by layer as well, but they use electron beam. Again, this is actually from metallurgical perspective, this actually advantage for some high sensitive for oxidation material like titanium. So this will perform in near vacuum condition. So you don't need to worry much about the oxygen content, and useful for reactive material, as I said. But again, this is more expensive process than laser. But now there's some company trying to reduce the price of this match with the LPBF. Again, still the research correct from the microstructure perspective. These two processes provide different microstructure. I will have a slide to show next. So, for example, this is our application. When I say material process, and then we need to say application, what is the application of this? So they also use already in NASA is a rocket chamber here. So, I mean, different model. I don't know much about that, but just to show you, this is what has been used already. And this still, in powder-based fusion, is still some challenge. Again, when I say challenge, I want to combine with the melting-based additive manufacturing process. And these include, but not limit to, the direct energy deposition, or known as bronze powder, and the powder-based fusion, or previous called SLM, or selective laser melting. So some challenges to control microstructure. Let's see here. This is the DED, or direct energy, and this is LPBF. You will see that this is actually from Fraunhofer video here. You will see deposit material layer by layer, and this is a thin wall section, supposed to be like to repair a turbine blade. And then you will see it will be a lot going on. I will show you in the next lecture here. And then this is the LPBF, which is laser-based additive process. This is very first publication of mine, published in Acta Materia with some experimental people. So this is the effect of layer thickness. If you choose wrongly, you will end up with the subsurface porosity like this. It's just small different, but you will get the surface roughness so different. I mean, this is actually the work started in 2013 and published in 2015 in Acta, and now it's received more than 1,000 citations. It's the most citation of my paper so far, this one. And then another challenge is actually, this is a surface porosity or cracking challenge. And if you print this one using Inconel 718, this is the raw nickel-based superalloy. Again, this is a commentary in Nature Material. They say the policy needed for these additive manufacturing to make this part in order to make from A to B, which is looks surface finish, look good, but this is using some surface treatment. But again, if you not worry about surface, you not worry about microstructure, but the next thing you worry is about distortion. If you use neutron tomography to scan it, and you compare with the CAD model or computer-aided design model with the real print, you can map the differences of the location. And this is the purple one is mean high distortion. That means there's some part need to be taken care of. That means future is that we want to probably doing digital twin or correcting on time, on fly. Yeah, this condition actually, you distort by this bit, you collect it, something like that, a closed loop control. Again, this is, in order to do that, we need to understand the process probably much better. So when I say now, I'm scaling down and down and down, going to the very, small scale. So this is a processing science of that. So this is actually the same as previous result, and this is type 6-4. So we print it and then we test it. We try to predict the subsurface porosity in this single track printing. And then this published in Scripta, Acta, and then in a ComMat side. Yeah? So we know that the processing complicated, even in this length scale already. But if you go into the very detailed length scale using the X-ray imaging here, you will see that the way the metal melt is quite different from the way you introduce into the model. So that means probably in order to close the gap of this one, the science needed for additive manufacturing. That is my research area, actually. So we need to understand from this local melting condition here to making the big part that can fly on air. And this is the way we know how to melt it. That's we will know how to control microstructure and property. And that means the complicated physical phenomena can occur in this micro length scale here and give rise to defect formation, which is already proved in many applications. So AM or additive manufacturing modeling is key to gain better understanding of the process in order to control this microstructure and design a property that we want. So this is actually commonly used for nickel-based superalloy. I mean, I show an example that's happening around the world from, this is Oak Ridge National Lab, like what I showed before. X1 is a 615 turbine blade USA. SpaceX also use Inconel version of that. I mean, Siemens uses for gas power generation, CM247. They claim that they can print defect-free, which is, this is non-printable actually, but we can print it at some condition. And then there is a fuel nozzle as well, GE. You'll see the part here is a little bit more complicated than the one flying 2013-14. And this is a rocket engine injector from NASA. It is all a high temperature material. So in order to summarize and then try to link to the next session, I want to say that AM, metal AM especially, is specific for application. But yeah, it's limited at the moment. The commercial standard, especially superalloy, is used for this, used for aerospace and energy sector. Successful adoption of this actually requires fundamental understanding, like I said previously, especially understand of the linkage of process, structure, property, relationship. And then experimental method is based on trial and error, and it's very expensive. So we need to get insight or provide insight into the process using computer simulation sometimes. So it's not probably, we may be able to solve something easy when we dealing with some complicated equation, which you will see in it from the next lecture. And then computational design or alloy design or material design is probably key. And then I will show you as well from today, probably today or tomorrow. And then, I mean, this is the nickel-based superalloy. You will see that they since the first inception, there's so many processes optimized for different composition. So even one class of material, and now they have more than 200-300 grade available on the market not include the one in research. But because the aerospace and energy is so important sector, as you know, and this is actually emerging rapidly since the prototyping in 1990, sorry. The global market actually is actually not, probably is about right, 30 billion by 25, but actually 80 something million by 28. And this one is actually, now we're trying to think about sustainability aspect. So it's reduced manufacturing cost by 170 to about 600 billion US dollars. And then that's this total energy supply reduced from 2.58 to 9.3 kilo, that this issue here. And then carbon emission actually can be reduced up to about 525 million tons by 25. So this is a sustainability aspect that I think we need to think as well for our future environment. And then that proved that in this area, I did a little bit research in the nickel-based superalloy, and you will know that from the research up until 2020, it's about 1,000 publications. But if you talk about AM overall, we have about 17,000 publications. So metal AM is quite limited. It's about only 10 times lower than the normal additive manufacturing impact for the future. That's why I choose to do it in this area. So nickel-based superalloy, a lot has been studied by US, UK, European, Indian as well, and also in the Far East. And the experimental is based on trial and error. So we may want to do simulation. And then from my research, the simulation model of paper just coming out not too long ago, less than 20 years ago. So, but my entry into this is about 2013. So it's quite early in my area as well. So I still keep working on it. It's a lot of things, a lot of interesting to do. I can promise you something very science, yeah. And then there's a lot of big room for research. As I said, even just one class of material, restricted to this high temperature application. Again, the characteristic of the process, as I said, I talk about publication, talk about the characteristic of process in terms of process and material. Using modeling and experiment here is an interdisciplinary approach. So you need to understand both of them in order to successfully implement that into the technology. So for example, give you some best processing window for to avoid excessive porosity, to avoid liquation or certification cracking, excessive distortion, strainage cracking. All these are metallurgical effects that can happen during printing. But how can we take into account all this in our design or doing engineering the material, engineering the process? That is the question. So ability of additive manufacturing is based on, definitely at the moment, my argument is that based on weldability. That's why I said we need to make a clear difference. It's not similar completely. So I have some paper published in additive manufacturing telling about additive manufacturability. And then anyway, there's some specific composition design that you can achieve some target. But again, you need to capture correct characteristic of the process. It's toward the end of the slide now. The trend now, again, we said about the milestone since the first machine that commercialized in about 1986, 87. If you remember first slide, now we're talking about not only prototyping of commercial customization. We're talking in the bigger scale, larger scale for the production. But again, we expect the leap of this technology actually by not too far away from here, 2025, 2030, something like that. But the next future, we need to talk about the combination of this with digital twin, with the robotics. The combination of the human-centric kind of approach. But again, that will be something for the later matter. So, and this is the trend in additive from NASA slide. As I said, they can use thermal imaging, big component, big part, and then print without our control microstructure. Or you can actually, how to say, use this additive part for controlling the surface as well. The remaining challenge is still, I come back to this slide that I will use for the next session. It's about the interaction. It's about the interaction at the lower length scale. So I think it doesn't show very well, but this one will show the melt pool. What is the liquid metal actually doing or happening during the process? Or this slide, this is Y-arc, so you will see clearly the spark of this one, when the metal deposit on this one, how the material deposit, how the temperature distribute, and how this fluid flow will all influence of the microstructure that emerging and hence property. And this will be the topic of the talk for this course, basically. I hope this is not too scientific, but I hope this will be useful. And to summarize this one, I want to say opportunity and challenge from one of my NatureCom papers, saying that we have both technological challenge and both scientific challenge that we need to solve in order to enable this technology for the future. So this is not inclusive anyway, but there's a key challenge that people looking at. For example, in the industrial perspective, they are looking at some in-situ monitoring system like thermal imaging to correct something wrong on fry, or some NDT, which is non-destructive testing qualification, like in the implant. You want to know where is the defect or significant porosity without any destructive method. Yeah, I mean heat treatment or pros treatment or heat thermal imaging and thermal management also important. Again, this is component manufacture is still challenge. How to make a big part without distortion and correct microstructure. From the scientific challenge, how to make powder is also challenge. Anyway, it's so expensive now. Atomization is so expensive. How can we reduce the cost and with control quality? The smaller the size of the powder, the more expensive of the kilogram per unit volume you get. And then heat source powder interaction is actually still a challenge as a function of material as well. Something we call from the metallurgical or material side perspective, the challenge is still remain in the hierarchical microstructure, because some material has some hierarchy in the microstructure which has not been fully studied yet. There's some paper from Max Planck Institute, for example, that they're looking at very thoroughly in the steel, but not all the class of material. And again, as I said before, it's specific to the application and the material and the processing route you use. So heat transfer and probably composition change, that is another challenge that I'm trying to tackle, which is, for example, if you have some composition which is material A, but finally you're printing something material B at the end, because the nickel actually lost by few atomic percent, which change totally the phase transformation that you want, let's say, in the 19 nickel titanium. There a paper published already with University of Birmingham saying that nickel can lose up to 2 atomic percent. That change the transformation temperature, Mechanistic transformation temperature in the body, 37, for example. And this will be very dangerous to put this part in the patient, right? Because it doesn't work in the condition needed. Yeah, that is why we need to be careful. Some material actually prone to very vaporization, composition change. It's not it's difficult to tackle, I believe, but yeah, there's some research going on. Defect formation is still an issue. Cracking, distortion, or blah blah blah, or surface roughness. That's what we're going to talk in the next few days. And having said that, I would like, I think, probably not over too much, but sorry for probably fast presentation. Next lecture in this afternoon, we'll talk about what is the physics happening in the process and how can we model it. That is the thing. And then what is a critical unsolved problem from scientific and technological perspective that we need to look at or do research? And then probably not today, but in probably later date, I will talk more about how can we link this or characterize the processing microstructure property relationship from a material system of interest. And having said that, thank you very much for listening, and any question before we close this lecture? If not, thank you very much.
We'll assemble back at 2 o'clock after the lunch. The lunch is arranged at the Kalam International first floor, right? And 3:30 we'll have a group photo, but don't miss. So by 3:30 during that break we'll have a group photo that is in front of the library. We have to move a bit from here. So all are available at 3:30 for the group photo. Thank you.
Thank you very much. I hope this is setting the scene.
Yes, yes.
Eagerly waiting for the next lectures, sir.
Say again?
Eagerly waiting for the next lectures.
Sure. Thank you. Yes.
I have a question.
Yes, sure.
We are printing Inconel based super analysis.
Which Inconel?